So hello everyone. So this is the second talk of our series this semester, and today we have the pleasure of having Sean Raymond give a talk for us. He's one of our collaborators, international collaborators, and he is a research scientist or a CNRS researcher at the Observatoire de Bordeaux in France. He's originally from the United States, correct? Yeah.
Yeah.
And he did his PhD in astronomy at University of Washington in Seattle. But he has been then for a long time already in Bordeaux or in France, and then went back to Colorado for a postdoc and everything. But now he is in Bordeaux. He is an expert, a world expert in the formation of the solar system, of gas giants, also the terrestrial planets. Has done a lot of work on delivery of water to the Earth. I saw also that he has a very interesting planet blog website with a whole bunch of videos. This looks like dozens of videos, right? That are explaining in quite nice terms kind of the basics of all of this, even for the general public. But I think this is even things that could be very useful also for researchers or young researchers at any level. So anyway, today we have him for this TEPS seminar. And he's going to give a talk on the formation of the solar system. And yeah, I think there's going to be an overall general background on this, and I think this fits perfectly in what we want to accomplish here. So I would say we let Sean take over.
Oh no, it just froze.
And I think he's going to share the screen with us. And the general procedure is that we let him talk, but also if there are some kind of questions that have to be asked during the talk, feel free to do this. But we'll also have some time at the end of this to have other questions. But feel free to interact with Sean. So I know I've also given the talk in this. So Sean, the complication is sometimes that you can't necessarily, you don't see the feedback so much. So that's one of the disadvantages of this online process. But if we don't hear you, we will definitely let you know.
Okay, that's good. Okay, so I'll go ahead and start sharing my slides, I guess. I'll just say that you are in the unlucky position of having to see me with a mustache. I do that every November for Movember. So usually I don't look quite like this, but you're getting
that's still a Colorado thing that you got used to.
Yeah. So anyhow, that's the thing.
Yeah.
All right, I'll go ahead and share my slides. Here we go. So I'll go like this. So can you guys see that okay?
Yes.
Okay. So my goal with this talk is just to kind of give you kind of an overview, a big picture view of global modeling of planet formation. So covering a lot of different things, and it'll be kind of a at a very high level in terms of like the general ideas. And I won't go too much into many details, but you're welcome to ask about that if you'd like to know more. So the title of the talk is Solar System Formation in the Context of Extrasolar Planets. And so the goal here is to really understand within, these thousands of examples of planet formation, which, I'm talking about extrasolar planets, how does our solar system fit in? And how can we understand both its formation and kind of the different diversity of other outcomes of planet formation? And I'll mention, my collaborators on this work at the bottom, especially Andre Isidoro and Alessandro Morbidelli. So here we go. So you guys all know the solar system. We got our 8 planets. Now, if we want to put the solar system kind of in a bigger context, you can ask the question, well, if we were to view the solar system as an extrasolar planetary system, what would we see? And of these 8 planets, the only one we would see or have a hope of seeing with at least a decade of radial velocity measurements is Jupiter. And what we know about Jupiter, if we monitor the sun as another star for 10, 15, 20 years, we would have a radial velocity signature of Jupiter that would give us Jupiter's mass, or its mass sin I at least, the shape, the size and shape of its orbit. And that's all we would know. So basically the solar system around another star is just the Sun-Jupiter system. There's nothing else that we could see. And so based on this and what we know about exoplanets, how can how can we put our solar system in context in terms of occurrence rates? So this slide just kind of shows in a very simple way some exoplanet demographics. So starting from the top with kind of sun-like stars, in quotes, stars that are roughly solar type, the thickness of the line here corresponds very roughly to the occurrence rate of different outcomes. So starting at the top here, I wonder if I can point. Can you guys see my mouse if I move it around?
Yep, we can see it.
Okay, so I'll use my mouse as sort of a pointer then. Hey, Nick, how's it going?
It's going well, thanks.
So using my mouse as a pointer, so starting up here at stars, you kind of come down, and so got these stars, and you can ask the question, what fraction of sun-like stars have gas giants? Say like Saturn or Jupiter-ish mass planets, and the answer is about 10%. So that takes you to the left, and so the line gets a lot thinner. Then you can ask another question, which is, what fraction of those systems with gas giants have orbits that are similar to our own Jupiter's? That is, relatively wide orbits that are pretty circular. And it depends exactly how you slice it. But it's something like 10% of those have, Jupiter's on Jupiter-like orbits. And so in very simple terms, that would put the solar system, the Sun-Jupiter system as about a 1% occurrence rate among sun-like stars. And if you go down other branches, for example, systems that have Jupiters on very different orbits, they often have very stretched out orbits. Once in a while, there's hot Jupiters out there. Systems that don't have gas giants, or actually some that do also, often have super Earths or sub-Neptunes, something like half or more of all main sequence stars have these, so they're very abundant. And so the goal here is to take this kind of cartoon of the demographics and make a corresponding little map of planet formation, where you can kind of say these things happen, then this special thing happens that is what I would call a bifurcation. And that splits into different branches of outcomes with the goal of explaining kind of different diversity of what can happen and what events we think must have happened to get to our own solar system. And so we're kind of basing it on the observations, but it's a kind of a planet formation model-y thing. So just to get started, we think that planets form in protoplanetary disks that are mostly gas with a little bit of dust. And the first key step is dust grows into little bigger sticks together and drifts around within the disk, and then it can clump. And simulations of this kind of process show that there are these different hydrodynamic instabilities. The strongest one these days is thought to be the streaming instability, but there's other candidates for these kinds of instabilities that can basically take millimeter to centimeter sized particles and concentrate them enough that they become self-gravitating planetesimals. And so directly from things that are, say, millimeter size that grew from dust, you can end up with 100-kilometer scale planetesimals. And when people talk about planet formation, they often start with the planetesimals, but there's a whole story to how they got there. The next step of growth is planetesimals growing into the bigger things. And so we think planetesimals, probably form throughout the disk, but maybe not totally evenly, but we'll get to that later. Anyhow, any planetesimals that form really close to the star are probably rocky because there's no ice to get incorporated in them while they're growing. But past some critical temperature that we call the snow line, they're likely to have, maybe half rock, half ice, something like that. And the next phase of growth is these planetesimals grow. They can grow by bashing into each other. They can also grow by grabbing onto those leftover dust particles, leftover dust, and what's called pebbles that are drifting continually through the disk. And this process is way, way more efficient past the snow line, such that starting from the same planetesimals, by the time Mars mass planetary embryos grow in the rocky part of the disk, the embryos that grew further out are maybe 5 to 10 Earth masses. And so just starting from the same stuff, you get this division where you have much more massive guys a little further out and smaller ones closer in. And this is just because of the efficiency of pebble accretion, we think. So now this gets us to this first bifurcation that I was talking about. So let's say that no Jupiter forms, okay? So no gas giant forms in the system. What might happen next? And our models suggest that you might end up with a lot of super Earths. And so here's kind of just a few examples of super Earths that are out there. This plot's showing the x-axis is just the logarithmic period, and the solar system's terrestrial planets are shown in the bottom there. And what you see is super Earths, basically, this shows their kind of rough sizes, or they're typically, between the size of Earth and Neptune, with a certain distribution that I won't get into. And they're often on in orbital configurations that are relatively compact. So here, the kind of the distance between any two planets is a measure of how close the orbits are, right? You can measure their as their orbital period ratio. And so if you look at the distance kind of, for example, between Earth and Venus, which I think I mislabeled here. These words are in the wrong place. But anyhow, Earth and Venus are the second and third planet from the sun. And so that distance in this kind of plot corresponds to the period ratio. And you can see that that's kind of typical of the period ratios among these super Earth systems. Now, if we want to kind of reproduce, a goal of this kind of modeling is to reproduce what we see. And so what do we see with the super Earths? Well, we could try to reproduce individual systems, and sometimes we do. But on a general level, we want to reproduce broad kind of properties of the global population. And so there's a couple of these. I'll just use a couple of the ones that we use the most. One of them is the period ratio distribution. So what this is basically anytime there's a system with at least two planets, you take the ratio of the orbital periods of every pair of neighboring planets, and you just chuck it in a box. That's the period ratio distribution. And here's what it looks like for Kepler planets. And so it's not that interesting. What does it look like? Just kind of a smooth curve. Right? What do you get out of that? Well, what you can get out of it is what it doesn't look like. It doesn't look like this. Right? If it was a staircase function like that, that would tell you that most systems are in resonance. So in this example, half of all planet pairs are in one resonance called the 3-2, and half are in the 2-1. And so you end up with this nice staircase function. You could easily have other resonances and you get a different staircase. But you get the general idea. Most systems are not in these resonances. So that's an important constraint for models. Another constraint is just how many of them you see. And so the multiplicity distribution is just saying, of all the systems we see with at least one super Earth, planet up to 4 times Earth's size, how many planets do we see in a given system? And it's tricky because this is biased based on which ones you can see, but it's a constraint that has to be matched by models. And we'll get back to that later. So a key ingredient in these models, starting from this phase where planetary embryos have formed and are, at least a few Earth masses in size, is orbital migration. And so migration is one of these things that a lot of people don't like too much because, to be honest, a lot of the details are not that well known. There's a lot of little tricky things that depend on exactly what the disk structure is right in the right spot. And so the details of migration, they could change a little bit, but you can't avoid that it happens. Every single study that I basically ever done of this kind of thing, of planets inside a disk, there's density waves that are launched. Those waves torque the planet's orbit and cause it to migrate. Okay? So this has to be included in models. It matters for planets above roughly an Earth mass or so. And the more massive the planet, the faster they migrate. And so in this image here, you can see there's actually 5 different planets embedded in a disk in a simulation done by Arno Pierens. And they're each, I think, 3 Earth masses in this case. And you can see they launch all these pretty spiral density waves everywhere. It's really pretty to look at these simulations. Okay, so migration is going to be a kind of a key ingredient in these models. And migration usually goes inward. And so one thing you might imagine is, well, if planets form really fast and migrate inward, maybe they just fall on the star. And that would be a nice idea, but it's not right. Because we're quite confident there's a lot of lines of evidence that show that there's inner edges of the disk. Okay? The disk of gas doesn't go all the way to the star. The inner edge is typically at something like 0.1 AU, something like that. And so any planet out there can migrate in. It can migrate in fast or slow, depending on the conditions, but it's going to stop at the inner edge because there's a torque that balances it right at the inner edge. And so any planet that's going in is going to stop there. And this matters because if everything was falling on the star, then you'd be losing a lot of mass. But if everything's going in there and stopping, it's a way to basically mass load the inner part of disks. Migration can basically take big things and move them inward. And that can possibly explain why there's so many massive things close to their stars. So let's go back to our kind of cartoon picture of this. And I just want you to know that these cartoons are not dumbing things down at all. Right? This is how I give talks to specialists too. And even this is how I think of it usually, is just in cartoon form. So cartoons are really state of the art, trust me. So cartoons, so back to our picture. After this phase of petal accretion, it's never quite as pretty as this. But the general idea is we think that you have smaller rocky embryos closer in, larger icy ones further out. But they're still embedded in this gas, this thick gas disk that's going to cause migration. And so migration should do something roughly like this. In our simulations, things migrate inward, and they end up at the inner edge of the disk. So once one guy reaches the inner edge of the disk, the next one's coming in. They don't just crash into each other. They tend to get trapped in resonances. And they usually end up forming long resonant chains. And sometimes the chains go unstable and there's a collision, but as long as the gas disk is there, they just reform another chain. Doesn't matter. Okay? So this is kind of a generic thing. It's really hard to avoid this outcome. We always get these resonant chains. But the resonant chains are held together by the gas disk. The gas disk is kind of like the teachers at recess that are making sure the kids aren't doing anything too stupid anyway. Right? As soon as the teachers go away, the kids go crazy. So as the gas disk dissipates, usually these resonant chains go unstable. And so that happens after a few million years. The resonant chains go unstable. There's usually a phase of collisions and close encounters. And the final systems that form are generally more spread out than they were before, and they're not in resonance anymore. This is what happens kind of generically in simulations. And so going back to the period ratio distribution as a constraint, right? This is our not too exciting, real distribution. And here's what we get from real simulations. The red curve is basically a staircase kind of curve that I was talking about. These are resonant chains that we form naturally. And so you can see they end up in kind of characteristic resonances. Sometimes they're in 2-to-1 here. I don't know which these ones are. Is that the 3-to-2? Anyway, it's not important which ones. They end up in characteristic resonances. Then when they go unstable, they produce the blue curve. The blue curve is those more widely spaced super Earths afterwards. And so the simple thing is to be open about it, our simulations don't always get the right ratio of stable to unstable ones to match observations. But if we say that we can kind of characterize those two outcomes, then we can say about how many of each type are needed to match what we see. And the answer is we need something like 90 to 95% of systems of those resonant chains to become unstable to match observations. And so once, depending on the conditions in simulations, sometimes we do get that, but not always. All right, and so that's interesting. So according to this kind of way of thinking, forming these nice, pretty resonant chains is really a generic thing, but usually they don't stick around. But once in a while they do. And when they do, they're really cool systems. Like, for example, TRAPPIST-1. This in this way of thinking would be a surviving resonant chain where all 7 planets are in orbital resonance. So it's a really kind of a pretty one. This would be a rare one that survived. And the same, I won't go into this in detail. The same kind of types of simulations also match the multiplicity distribution, what's sometimes called the Kepler dichotomy. The idea being that there's a big spike. Most systems that we see only have a single detected super-Earth. That's this gray line here. And our simulations naturally reproduce that when you have something like 90% unstable resonant chains and 10% stable ones. And the reason being that late phase of instability excites the inclinations between orbits so that you often miss the transits of multiple systems. So basically, according to our model and these kinds of models, this peak at one planet is not real. It doesn't mean that most systems really only have one. It means that in most systems you can only see one, even though there are other ones. All right, moving on. So now going back to our kind of global picture, let's take the other route in that bifurcation. So what if a Jupiter does form? What are the consequences? So back to the same cartoon. Let's say this innermost big ice-rich embryo gets big fast enough to accrete gas. It naturally grows and piles on a bunch of gas and carves a gap in the disk. Okay. And so what does that do? Well, there's some interesting consequences of that. One thing is that once that gap has formed in the disk, it blocks other guys from getting in there. And so there's other more distant super Earths, or large planetary embryos that are trying to migrate inward are blocked by Jupiter. And so what does that mean? That means that a Jupiter-like planet is essentially protecting the inner parts of its system from those distant icy invaders. So there's there's other large embryos that would otherwise migrate inward to become super Earths. They can't, so they're blocked. So they stay out and become ice giants or something like that. And so in this way of thinking, in this model anyway, things like Uranus and Neptune would have been failed super Earths. So now let's keep going on this picture. Let's look at systems that do form Jupiters, but that don't end up on orbits like our own Jupiters. So here's a distribution of the orbital eccentricity versus orbital semi-major axis for giant exoplanets that are known. Excuse me. And I included Jupiter on here for scale. And as you can see, and as many of you know, there's a very broad range in the orbital eccentricities of these planets. So there's a clump in here of hot Jupiters that generally have pretty circular orbits, and we think that's because of tidal interactions with the star. But past, a tenth of an AU, the median eccentricity is about 0.25. So it's really high. So planets that are on low eccentricity orbits are pretty rare. And so we think that there's kind of two key processes shaping this diagram. One of them being migration, in this case of larger planets, not of the small ones. And the other one being planet-planet scattering. So this little cartoon here is showing a system that started off with two Jupiters on concentric circular orbits that went unstable, and one of them was kicked out, and the survivor has an eccentric orbit. So let's look in a little more detail. So in our cartoon, again, after the Jupiter forms, carves a gap in the disk, it doesn't just stay there and not do anything. Even though it can hold back the migration of these other guys, this guy itself is still migrating too. And so if the Jupiter forms fast enough, while there's still a lot of gas in the disk, it makes sense that it should migrate too. It should migrate in and basically become a hot Jupiter. And that might be where most hot Jupiters come from. There's kind of a debate about that. And it would also affect any smaller rocky planets that could form, of course. Another thing is that anytime one gas giant forms, it makes sense that more than one forms. And they often end up migrating and getting trapped in resonance. Okay? So that's kind of a common thing too. And once they are in resonance and the gas goes away, you can have the same kind of outcome that we saw in those super Earths. And so here's a really awesome movie that I like that Eric Ford made. Here is a system with 3 planets. The outer 2 have kind of gravitationally jostled each other such that their orbital shapes have changed, and now their orbits cross each other, which doesn't mean they're going to collide. Instead, they have a series of close encounters. And the last gravitational encounter had a really strong scattering event, and one of the planets got enough orbital energy to get launched out into interstellar space, never to return. But the survivor has this very stretched out eccentric orbit. And so in this context, the stretched out orbit of that survivor is kind of like a scar from its violent past. And here's a simulation of this process. So this one is a real simulation this time. Here where you're seeing the axes are orbital eccentricity versus semi-major axis. And this is basically reimagining the solar system, but instead of Jupiter and Saturn, we have 3 giant planets, basically Jupiter, Saturn, and another Jupiter. And so closer to the star, there's a bunch of rocky stuff that's trying to form terrestrial planets. That's this colored stuff closer in. And further out, there's a disk of basically icy planetesimals that don't matter too much here. And you can see the movie slows down here because the giant planets are about to go unstable. Boom. And so this is planet-planet scattering. This is a giant planet instability that happened. I chose that one to make a movie from because it happened relatively late. Usually that happens earlier in the evolution, but it's kind of nice for explaining. And so what happened here is all of that nice rocky stuff that was in the process of trying to form terrestrial planets got dumped onto the star. All that outer icy stuff, that was not too important here, but that would be comets, got ejected. And the surviving giant planets have really eccentric orbits. And so this simulation basically took a system that looked a lot like the solar system, and through planet-planet scattering, turned it into a system that looks a lot like exoplanets, giant exoplanet systems that we know. And in the process, destroyed all that nice rocky stuff, which is a bummer. So now let's go all the way to go through the bifurcation of having a Jupiter and also a Jupiter on an orbit like ours. So here I'll go into kind of some detail of models for how we think the solar system may have formed. And so the bad thing about the solar system is there's only one. The good thing is that we have a lot of constraints. And so just zooming on the inner solar system here, what do we got? We got our 4 terrestrial planets, we have an asteroid belt, and for this example, I'll cut it off at Jupiter. Okay? And so how much stuff is there? The terrestrial planets add them up, they're about 2 Earth masses. The asteroid belt is almost empty. There's less than 1,000th of an Earth mass in there. And there's Jupiter. But there is some structure in the asteroid belt. You can see in the little dots I've drawn, there's a couple more red ones closer in and a couple more blue ones further out.
No worries. Sean mentioned that could happen, but he's going to be back in 30 seconds. So maybe you have some time to think about all the things he said already.
This is a great review of.
Yeah, I like it.
Planet formation has evolved since I took a grad course on it, so this is good.
That's right. All right, Sean, there you are again.
I'm back. Sorry, that's annoying. All right, I'm sorry about that.
No problem. We talked behind your back while you were gone.
I hope so. I hope you made fun of me for this kind of thing. All right, I'm back. So I think, did you guys get to the part where I was talking about the asteroid belt and stuff?
Yes.
All right. So I was just saying there's a lot of structure in there. And as before, the goal of modeling this kind of thing is to reproduce it. But we're not going to try to reproduce every bump and wiggle in there. The goal is to reproduce the broad scale things. And so the kind of constraints that our models try to reproduce are things like these yellow things that I've listed, like the number and the masses of terrestrial planets, their orbits, how fast they grow. And then, but since they're right next to the asteroid belt actually provides nice constraints on the dynamics also. And so ideally we want to match the total amount of asteroidal stuff, the dichotomy between those red and blue guys, and their rough orbital distribution. And so the kind of the what we call the classical model of terrestrial planet formation is very simple. The assumption is that you can decouple terrestrial planet from giant planet formation. And so we know that gas disks don't last very long. They last only a few million years, whereas Earth is known to have taken at least 50 or 100 million years to finish its growth. And so the classical model basically says, let's just say that giant planets were already completely formed by the time terrestrial planet formation was going on. And so in this simulation, it kind of time zero is when the gas disk is gone, and there's a whole bunch of small rocky things, kind of mini embryos that are going to bash together and grow. And you'll see what happens. So you can see that the color here corresponds to water content, with red being dry and blue having 5% water. And so what you see is kind of the whole disk gets excited. It self-excites from the inside out, and it gets kicked by Jupiter from the outside in. And you can see there's kind of mixing that happens between different zones. Every time a color changes of an object, that means that its feeding zone got wide enough to encompass things that started with different colors. And so the guy right around 1 AU here is a pretty good Earth analog. And you can see its color just changed. That means that it got some water that originated basically in what's now the outer asteroid belt. And so that's kind of where water came from in this model. And by within 100 million years in this kind of simulation, you typically form 3 planets. In this case, we have pretty good analogs to Venus and Earth, and a quite bad Mars analog. This Mars is way, way too big, and it's not in the right place either. But not being in the right place is a detail. It's way, way too big. And so what happens if you run many of these simulations is you can have a distribution of outcomes. And this plot is just basically showing the masses of different planets that have formed in simulations versus the orbital separation. And the real terrestrial planets are the squares, and the simulations are the little circles. And so you can see we're not too far off from Earth and Venus. This is a linear scale. So linear scale wise, it's pretty good.
So these are many simulations together, so many simulation outcomes together, right?
Exactly. Yeah, this is some number of simulations. I don't know, 10 or 20 or something.
Mm-hmm.
And so the key problem here is Mars. So Mars is this guy right here. Mars is really only about 1/10 of Earth's mass, but the simulations tend to produce Marses that are more like 5 to 10 times that mass, closer to Earth's mass rather than to Mars's true mass. And you often end up with Mars-like things that are further out in the asteroid belt at a 2-3 AU, where they shouldn't be, where they're not. And so this has been an issue in terrestrial planet formation stuff for a long time. And at the moment, there are actually 3 potential solutions. And we don't know which one is, actually, I shouldn't say which one's right, because none of them could be right. But we don't know which ones are wrong. And so let me go through the 3 of them. So I'll explain each of them in some detail, because they each have different pieces that are quite interesting to think about. So the first one's called a low mass asteroid belt model. Second one's the grand tack. And the third one's the early instability. You may have heard of the grand tack. That's the best known of the 3 models, because it's been out there the longest, basically. So the low mass asteroid belt model basically just says, well, in those cartoons I was showing you before, there's always a nice smooth distribution of planetesimals. But is that realistic? We do think that the distribution of gas and dust were probably smooth in disks, at least at the start. But does it make sense that they should stay smooth forever? Well, we have some images, like, especially with ALMA these days, has taken several really pretty images of young planet-forming disks that are, at the age when they should be forming planetesimals. And none of them look smooth. Yeah, they all have rings. And what are these rings? These are kind of clumps where dust is drifted and clumped in certain orbital distances. And there's other distances nearby that have a lot less dust. And so based on that, it doesn't seem, it seems like maybe those rings where dust clumps could be where planetesimals form more readily also, and fewer would form in between. And so let's just say, based on this, it's possible to imagine that you could have had a ring of rocky stuff around Earth's orbit, but very little in the asteroid belt. And that's the basis of the low mass asteroid belt model. So the idea is that there was maybe a ring, this red ring of rocky stuff around Earth's orbit, very little in the asteroid belt, but then further out there was plenty of that blue stuff to grow Jupiter's core and Saturn's core and so on. So let's just say that's an assumption that this is possible. If this is possible, does it reproduce our solar system? And so here's what naturally happens in that case. From this ring of material, basically gravitational stirring is such that some objects get kicked out. So Mars would have been one that got unlucky, an embryo that got unlucky, got kicked out. And since it got kicked out of this narrow ring, it was kind of starved. It wasn't accreting any more material. Whereas Earth and Venus were within the ring, and so they grew big. And the same deal for Mercury in this idea also would have been kicked out on the other side. And so based on that, the model can match the terrestrial planets' masses. And so here's kind of just a plot showing that works. Here again, we're showing mass versus orbital distance. And the squares of the real planets, the symbols are simulations. Here it's a bunch of simulations. And you can just see that there's kind of the broad trend matches the distribution pretty well. Okay? Even though all the mass started in this narrow ring that's shaded in the middle. So that low mass asteroid belt works pretty well for getting the terrestrial planets right. What about the asteroid belt? Since nothing started there, why should there be much in there now? And why would there be a diversity in what we see? And the answer is because it's easy to implant things into the belt. And so the easiest of all ways to implant things in the asteroid belt is just Jupiter's growth. When Jupiter grew, it naturally scattered anything nearby all over the place. Anything that didn't bash into Jupiter got kicked all over the place. And some of that stuff ended up getting trapped in the belt, mainly through the action of gas drag. And just doing that can reproduce those blue dots, those outer C-type asteroids, and also deliver some all the way to where the terrestrial planets are growing. Of course, the terrestrial planets are also growing, and their growth also kicks stuff all over the place, and a little bit of that gets trapped in the belt too. And even though these processes are not that efficient, remember, there's not very much in the belt anyway, so they don't need to be efficient. And in the end, the asteroid belt and the terrestrial planets that you can get from this model match what we have pretty well. So that's that model. One small note on Earth's water. I'm not going to talk much about it. Sometimes I give whole talks on the possible origins of Earth's water. But since you saw that movie where in the classical model Earth's water was accreted from an asteroidal source, I just want to mention kind of the current thinking on this. So the total amount of water in the Earth is about 1 part in 1,000 by mass. And so this image, I really like this image that someone made of basically taking all the water on Earth and making a little sphere out of it. And it's this little sphere about the size of, I don't know, half of the US or something. And another key constraint here is the isotopic signature of the water, which is a really good match to carbonaceous chondrite meteorites that we think do come from C-type asteroids. And so this led to the old story that I was telling you before, that primitive outer asteroidal stuff delivered Earth's water, like in the classical model. So that's the old story. The new story goes one step back in the chain. And the new story is that water was delivered to Earth by the same population that was implanted into the asteroid belt as C-types. So Earth's water would not have come from C-types, but both Earth's water and C-types have the same parent source. And that source is probably beyond Jupiter's orbit. And it was probably implanted by Jupiter's growth and migration. That's the latest thinking on that. All right, moving along. The grand TAC model. I know I'm throwing a lot of things at you, a lot of different models at once. Feel free to ask questions or whatnot. I'm skipping over a million details all over the place.
But Sean, this is really great. I mean, this is also what Nick and I just talked about when you were off for 1 second. This is like a really amazing review of planet formation. And Nick was also joking about how the time when he took a class in planet formation is a while ago, and lots of things have happened. And so it's really great to see this here. I think for us and also for all the students and postdocs, I think it's a very great review.
Oh, cool. Well, thanks. And yeah, so I'm throwing out a lot of terms, a lot of ideas that each has its own history and lots of depth to it. But I'm just kind of talking about the high level stuff.
Mm-hmm.
All right. So moving on, the grand TAC model. This one is the best known, I think, of the terrestrial planet models at the moment. And it's based on the migration of Jupiter and Saturn together. And so this image is showing a snapshot from a hydrodynamical simulation of Jupiter and Saturn migrating together within the disk. And so there's a little bit of slightly technical stuff here. But here's one possible outcome that's pretty simple of what Jupiter and Saturn would do in a gaseous disk. So here's a cartoon just showing orbital distance versus time. And Jupiter is growing as we go. So it's one of these simple ones where there's no labels on the axes, just conceptual. So the idea is Jupiter's core was growing somewhere. Once it reached kind of a critical mass of about 50 Earth masses, that's about the critical mass for a typical disk to start basically digging that gap and creating a gap. And there's a phase of very rapid migration associated with that. And then once Jupiter cleared its gap, it slowed down and went into this kind of migration where it has a nice gap and the disk is gently pushing it inward, which is slow but still inward. Right? At the same time, Saturn was probably doing this also, but further out. So Saturn was probably growing a little further out. When it reached this critical size for emptying its gap, it probably migrated in really fast. And like I was talking about before, that doesn't mean it collides with Jupiter. The most natural outcome is to be trapped in resonance. And simulations show that's either the 3-2 or the 2-1. Then there's a very interesting hydrodynamical effect that one planet on its own, Jupiter on its own, would migrate inward. Saturn on its own would migrate inward. The two of them, locked in resonance with the more massive planet being on the inside, can, under certain circumstances, go outward. Right? It depends on some details that you don't want to know about. But under a decent range of circumstances, I'm not just talking about a tiny little bit of parameter space, a good chunk of parameter space, Jupiter and Saturn migrate outward together. Now, if this model is going to match the true solar system, then at some point, this migration had to stop. And one reason it may have stopped is, the gas disk was just dissipating when Jupiter was at around 5 E. There's other possible things too, but that's the idea. So the grand TAC model is based on this evolution of Jupiter and Saturn. And so based on the giant planets doing this, what does it do to the terrestrial planets? So here's a little simulation that this one, I think Dave O'Brien made this one. So eccentricity versus semi-major axis. In this case, the green dots are planetary embryos, and the red dots are planetesimals. And all we're going to see is basically starting from a disk of stuff, you're going to see the creation of a ring because of Jupiter. And so these things are all kind of growing and stuff. And then you see Jupiter come in there, migrate inward, turn around and go back out. And so a key parameter in the model is that turnaround point. And so kind of the part in the grand TAC model that's really put in by hand is where Jupiter turned around because Saturn caught up to it. And so that's put in by hand, and it has to have been between about 1.5 and 2 AU. But in that case, you can see what happened. This disk of stuff in here went from a continuous disk, it got smushed into a ring. And so in the end, the conditions here you have, basically there's a rocky ring of material that looks a lot like the one in the low mass asteroid belt model, where we kind of invoke that as just kind of being a signature of how planetesimals formed. In this case, it's actually created by Jupiter's migration, inward and outward. And based on that, here's another one of these mass versus semi-major axis plots of many simulations. This time the blue squares are the real terrestrial planets. And you can see basically the general distribution is matched by the grand TAC. The idea of having a big Earth and Mars, big Earth and Venus and a small Mars. So that works too. Now the third model is a very new one. It's only been out 6 months or something like that. It's based on the instability that we think happened in the outer solar system. It's sometimes called the Nice model. And the idea of this model is that the giant planet's orbits, when the gas disk dissipated, were probably more compact, and we think they were likely in resonance. And so the giant planets may have been in a resonant chain at that time. And exterior to their orbits, it's kind of invoked that there was this primordial disk, this primordial Kuiper belt that was much more massive. So the Kuiper belt today only contains, a few percent, 5-10% of an Earth mass. But we think it started off with maybe 20, 30, 40, 50 Earth masses, something like that. And so this animation here, you can see kind of the snapshot that you see right now has the orbits of just the giant planets, and all the green dots are outer planetesimals, outer icy things, kind of this primordial Kuiper belt. And it's been invoked for a long time, since 2005, this model first came out, that an instability was triggered in the orbits of the giant planets because of interactions with the planetesimals. And that is what, that was basically responsible for shaping the giant planet's orbits. So here's the animation here. It's kind of counting down to the instability. The instability is triggered there. And you can see one planet, during one snapshot, a planet had a really, eccentric orbit. That was an extra ice giant that was included at the beginning. If you counted right, there were actually 5 giant planets instead of 4 at the start. And the reason that's included is because these instabilities almost always lead to the ejection of a planet. And so if you invoke that an instability may have happened, the simplest way to end up with 4 giant planets now is to have started with 5. And it's even possible there was another one, but it's simpler to start with 5.
So is the 5th one planet 9?
That probably
No.
Do you guys? That's a whole other thing to talk about. You guys must have strong. I can hear someone in there has strong opinions about Planet 9.
That was Brett Gladman.
Okay. So I wasn't even going to go on Planet 9.
Okay, all right, that's okay.
But that's an idea. So in what we're talking about here, there's this instability, and there's a lot of different lines of thinking as to why we think this really did happen. The giant planets' orbits, a lot of different properties of their moons, of the small body populations, especially of the Kuiper belt, that seem to be really well reproduced by this kind of instability. Now, what's different about this, you may have heard about this, over the last 10, 15 years even. What's different just in the last couple of years is the timing has changed. Right? This is kind of a thing. It was first created to explain the late heavy bombardment, which would mean that the instability had to be delayed by something like 500 million years after planet formation. And the idea was that those green dots basically, and destabilizing the asteroid belt, could explain the craters on the moon. There's reanalysis both of the craters and of other cosmochemical constraints that suggest that timing may not hold up. And so now, current thinking as of the last couple of years is that this instability probably happened, and it could have happened anytime up to that point. So it probably didn't happen at 500 million years. It could have happened from time 0, as soon as the disk dissipated, out to 500 million years. And so the third terrestrial planet formation model proposes that that instability happened early, that it happened basically within a few million years of the dissipation of the gas disk. And if that happened, then it can shape terrestrial planet formation and affect, the growth of Earth, Venus, and Mars. So here's an animation by Matt Clements, who's the lead guy on this model. And it's just like the ones I was showing you before, except he used a nicer color palette than me. And so you can see he goes from like kind of the dry things are kind of this pinkish color to wet being more blue. And time 0 here is kind of when the gas dissipates. And in this particular example, the instability is triggered at 10 million years. And so here we go. So you can see kind of the plants are growing. And it's the same as before. There's various kinds of mixing. It's not that different from the classical model until the instability happens. So there, the instability just triggered. And if anyone was kind of staring at the asteroid belt area, you'd see there was a big excitation and a whole lot of stuff got cleared out of the asteroid belt. And what happens, because of that instability, clearing out a lot of material from the asteroid belt, you can clear out a factor of 100 or 1,000, or basically deplete 99 or even 99.9% of the stuff in there. And what that does, it clears out a lot of the stuff that would otherwise end up bashing into Mars and growing. And so at the end of this particular simulation, we have pretty good matches to the terrestrial planets. These lines are showing where the actual planets are. And what's really cool about this model is it's matching the inner and outer solar system at the same time. And you get the best outcomes for the inner solar system when you match the outer solar system too. Right? It's pretty cool. Right? Again, like I was saying before, this doesn't mean that it's right. Right? It just means it's a cool model. It's interesting and worth looking in more detail. And just the punchline that I'm showing for each model is mass versus separation. Here it's red squares that are the actual planets, and you can see you get the broad distribution, and you generally get small Marses and big Earths and Venuses in this model also. So back to our kind of summary, we have 3 potential solutions to this small Mars problem, but they each work well, but they each have some little issues. And so let me just kind of summarize the key issues, which are sort of paths forward to try to falsify these ideas. So for the low mass asteroid belt model, the initial conditions are really the key thing, right? If you get a nice ring of rocky stuff, it does seem to work really well. It does match the terrestrial planets and the asteroid belt really well. Is that a realistic starting point? We don't know, but people are looking at this now. The Grand TAC model, the key thing here, at least one of them, is the outward migration of Jupiter and Saturn. And what I didn't go into the details is, but the key thing is Jupiter and Saturn can migrate outward if they maintain a mass ratio such that Jupiter is quite a bit more massive than Saturn. But if they're migrating out through the gas disk and they're gas giant planets that can grab onto more gas, then maybe Saturn should be growing more and they would end up as equal mass planets. But if that happened, they would actually turn around and go back in. That happens in some simulations. And so understanding how the interplay between migration and growth is something that's not that well understood, and people are looking at now. And the early instability model is kind of a neat combination of dynamics and cosmochemical constraints, because the only way to answer this is to really know when the instability happened. If it happened early enough, then it's a great explanation for why Mars is smaller than Earth. But if it happened too late, then it can't do it because it's too late. So we got to answer that question to see whether it could have affected the terrestrial planets. So kind of back to this kind of cartoony thing. In this simple representation, how do we form a system like the solar system? If you're taking into account the kind of the general ideas I was throwing out there, what ingredients are needed to form a solar system? And first thing is Jupiter must have grown relatively early to protect the inner solar system from these, other invaders. And a byproduct of its growth is also to sprinkle water on the growing rocky planets. Just a little bit though. Jupiter doesn't give it a lot, just a little bit. But Jupiter cannot have kept migrating inward too close to become a hot Jupiter. And so why did it not keep going in? One possibility was because of Saturn in the Grand TAC model. Some inward and outward migration is fine, but not too much. And of course, the giant planets' orbits had to stay stable-ish, right? So the solar system had this instability, but it was a really wimpy instability. Compared to those planet-planet scattering instabilities, to explain giant exoplanets, our instability in the solar system is super wimpy. And what would have made it not wimpy is if Jupiter and Saturn had scattered off each other. Because in that case, Saturn would have been ejected and the terrestrial planets would have been destroyed. So we know that didn't happen. But we still, so we're kind of in this in-between spot where it did have an instability, but it was a weak one. And, is that a common thing? Well, it depends on basically on the outcome of planet formation for these kinds of giant planet systems. And so an early instability is nice because it clears out the Mars zone and can explain why it's small, but a too big of an instability would have destroyed the terrestrial planets. So I don't have a clock going. So I have a few more slides about things like the interstellar object Oumuamua and ideas about that, but I don't have a feeling if I should stop here or keep going.
I think if we want time for questions, we might want to stop soon.
Okay, if we want to do that, so I can, let's see. So why don't I just skip the Oumuamua part, because that's, I can go on for plenty of time about that. So why don't I just stop and take questions here?
Okay, and maybe we have to invite you again, and then you can talk about this more.
Yeah, sure.
Yeah, so the floor is open for questions. As you can see, there was a lot of ideas that Sean put out there, and I would assume that there are a bunch of questions related to that. Are there any maybe questions from from anyone, basically, students, postdocs, professors, whatever is there?
I mean, I have a question.
Sure.
So how do people actually implement gas? Like, it sounds like some of these scenarios require doing n-body simulations coupled with gas, and that sounds hard. So how do people actually do this? Do you literally do hydrodynamics at the same time as your n-body simulations, or do you just have some sort of parameterized gas drag, or how does that play out?
So the answer is both. The simple answer is basically to do, as a first step, usually what's done is hydrodynamical simulations to basically calibrate forces in different conditions. Maybe, depending on the case, you can either use a simple, very generic power law disk, or get a better disk model. And then for the gas drag and migration stuff, most often it's calibrated to hydrodynamical simulations, but then imported as a simple recipe into n-body simulations, so you can run them for much longer. So it's kind of an in-between.
Two little technical notes. One, I just realized there's an option to raise hand. I apologize for not raising my hand, but that might be an intelligent way for people to indicate they have a question. And then I think Catherine had a question. I will read it. She says, I have to leave, but my question for Sean is this. Is it possible to form a large Mercury and then have it reduced in size later due to a giant impact? Mercury is not a normal terrestrial planet and may have been much bigger originally.
So Mercury is a big weirdo also. So I focused a lot on the small Mars problem, and it turns out the small Mercury problem is even worse. Because in dynamical terms, Mars is actually closer to Earth than Mercury is to Venus, and the Mercury to Venus mass ratio is bigger also, or smaller also. So it's also a problem. It's a similar issue because of its large iron content. Some people have invoked that it had some giant impact, that it started off more, a more Earth-like composition and then had a giant mantle stripping collision. It's very tricky. No one has satisfactorily matched everything at once. So a giant impact like that is totally plausible, and it's a natural outcome of planet formation. The trick is, in that case, it ends up much closer to Venus than it should. It's hard to have this kind of impact and then somehow separate the system at the same time. It's not clear whether it's just a rare, very rare thing, and once in 1,000 simulations you get a case where you have the right impact at the right time to separate things out, versus a totally different process that may have occurred. And some people are thinking about that, but there's really no satisfactory answer right now. And whether it's, so it's plausible that Mercury could have been maybe twice as massive as it is now, which would only make it Mars mass. But could it have been more massive than that? I don't know. So it's definitely an interesting one because it's also a clear connection to super Earths. You know, it's the innermost planet, and it doesn't look like super Earths.
I saw that Brad had a question.
Hi, Sean.
Hey.
Just a comment and a question. So I missed the very beginning, so I'm apologizing if I'm asking a question about something that you
No worries. No worries.
So I'll just comment that the belief that the requirement that you form at least Earth and Venus out of a relatively confined ring goes back 40 years to Weatherall and the first protostars and planets volume. And
yeah, the first reference I found for that is Weatherall 1978. I don't know if there's one before that.
That's yeah. So that apparent dynamical constraint that there's based on energy and angular momentum that you formed the terrestrial planets out of a narrow ring goes back that far. Related to this Mercury question, and I gave a TEPS seminar on things related to this a couple of months ago, explicitly. In all the simulations that I saw, you magically begin the planetesimals at about 4/10 of an AU. And obviously that's desirable because it tends, the imposition of the inner edge of that ring helps get planets that currently look like ours, and yet there's no physical justification whatsoever for the planetesimal disk to have stopped, to only have begun at 4/10 of an AU. And that may be related to this concept of, did we actually have super Earths earlier in our own solar system closer to the sun? Do you have any comment on that?
Yeah,
inner
so
edge?
that's a good point. I mean, the next phase of a lot of this modeling is looking at the previous step, like where the planetesimals come from. And, you know, studies to date, you know, just in the last year or two, show that the assumptions that everything forms smoothly across the disk is probably not a great assumption. And in particular, what's going on in the inner terrestrial part is really tricky. And so I mean, I haven't seen any study that satisfactorily makes systems that have planetesimal distributions that you can imagine reproducing the solar system. And so this is kind of a very active area of study, and I think it's a key thing to look at. I don't have any, you know, really deep answers about it, but I think this is, in the next few years, I think we'll have good, you know, progress on this front.
Yeah, well, the contrast with the extrasolar systems is pretty striking, where they have huge amounts of mass interior to half an AU.
Yeah. And that's very mysterious. And so this idea that I threw out there of Jupiter serving to starve the inner solar system by blocking the migration of outer embryos is an appealing idea, but it can't explain why there's no super Earths in the, you know, in a statistical level, because there's too few, you know, Jupiters in some sense to explain, you know, that, you know, basically the only systems that don't have super Earths would be those with Jupiters in that thinking. And so there's other ideas for how to starve inner systems to prevent the formation of close-in massive planets. For example, maybe you don't need a full Jupiter, maybe just the core of a Jupiter, like a 5 or 10 Earth mass planet, can block the inward flux of pebbles and, you know, starve the growth of planetesimals that are close in by doing that.
So we have one question also from a student. Prasanja, do you want to ask a question? And turn on the microphone first.
Hi, Sean. I'm a PhD student with Bjorn here in Montreal. I had a small question. I don't know too much about the instability model, but he said that you can see a factor of 1,000 depletion going on in the asteroid belt. I'm just curious, like if Mars is not growing, so where does that material goes out of the system, and does it?
That's a good point. So a large fraction. I don't know the latest numbers on this. I should know this. That I think Matt Clement's paper on this actually came out on arXiv like today. So it's like brand new, those numbers. And so some fraction of it, a good chunk of that is ejected in the end by Jupiter, and some fraction is pushed inward. Only a pretty small fraction actually collides with the sun. More often it's depleted by getting scattered either outward or onto terrestrial planet crossing orbits where it would eventually get accreted into the terrestrial planets.
Okay.
I maybe have one last question. So obviously this small Mars problem is like kind of in a bigger context with exoplanets, not only like the Mars problem, but also we want to understand this in general. But I guess what, if you had to distinguish somehow between those three scenarios, what observational evidence from exoplanets could help you to do that?
This is something we're thinking about now. I don't have a really good answer for you at the moment. There's some kind of simple predictions like, if Jupiter and Saturn, if the migration that's similar to the Grand Tack really happens, then you should not see, or at least not very often, planets with Jupiter Saturn-like configurations that are very close in. Right? Typically, planets that are where the inner one's more massive by a factor of 2 or 3. And the outer one is in resonance with it. They shouldn't be really close in because that kind of setup should have promoted outward migration. And the last time I looked at this, which was a few years ago, that held up pretty well. There were no close-in systems like that. I haven't kept up to date on that. And so this kind of thing can broadly test the predictions of these models. In terms of the rest of it is kind of looking at statistics of instabilities and things like planetesimal formation in rings. It's tricky to connect it. I mean, the goal is to make a very clear thing where if you measure this or discover this, then that model is out the window. And so that's what we would like to do. And some of the ways to address those are kind of theoretical, but hopefully some can be done in an observational way too.
Mm-hmm. All right, I think we are beyond the hour anyway. Yeah, Sean, thank you so much for this presentation. I think we have lots of things where people can study in more detail. I think it was a perfect overview for our level here of the different aspects of planet formation, especially with the solar system. Yeah, thanks so much. As I said at the beginning, Sean also has a nice kind of online setup where he has a blog with a bunch of videos, and I would recommend people that want to know more about specific things on planet.net to look into those as well. Also, in the talk, you've seen all the references. So if you want to know more about planet formation, feel also free to kind of go down that track of looking at these references. I would definitely look at Matt Clement's paper from today. I haven't seen it yet. Yeah.
I'll just mention real quick that Morby and I, Alessandro Morbidelli and I, had a project together, and kind of our final product was a bunch of videos that we put on YouTube. And so you can find them on this website, astrobiovideo.com or directly on YouTube. They're of us blabbing about several of the ideas I talked about.
Mm-hmm. All right. Then I would say we're done for today. And yeah, Anna is going to send out an email for the next one, but that's going to be in 1 month from now. All right. Thank you so much for you in Bordeaux, and see you everyone next month.
Cool. Well, thanks. It was a pleasure.